Hello, and thank you for joining me on Watch Mr. Coon Solve It. I don't know if that's a good title or not, but I'm going to go with it for right now. So what we're looking at here is exponential growth and decay. I'm using the human population as an example to build on for later videos. But to start with on this one, we're strictly looking at, is this an exponential model? Now, some models actually have the human population growing logarithmically, but here we're strictly going to go with a exponential model. So in 2002, the population was 6.2 billion. And according to this model, what should the population be right now? And actually, the question I'm asking is, what should the population be in 2019? But first, I want to look to see, is this model actually correct for right now? So what would P be? P would be the future population. So if we just stick in a value, say 6.2, e to the 0.03 times t. Now, time is since 2002 there. Well, it's 2018 is when the video was made here. So that's 16 years ago. So when I do that, I end up with a total here of 10.019. Now I went to, this is billion, of course. I went to world population clock. I just typed that into Google and I came across something, and it said that the population is actually much smaller than that. 7.6 billion. So the model's wrong. This model isn't an actual or a good predictor as it is right now. So what we need to do is we need to update this model, and that is easily done. So I'm going to put 7.6 at the future value. That's what the population is currently right now. 6.2 was the population we started off at in 2002. E to the point. Oh, well, we don't know the rate, do we? Because the rate is what's wrong here. So it's not point anything right now. It's just R. The time we do know, and that's 16. Now the question then becomes, how do we solve for R? Well, we'll start the same way we did before. Let's divide both sides by 6.2. Anytime we're trying to solve an equation, we start to unbuild the things that are around it. So when we do that, we end up with 1.22 equals e to the R times 16, right? Now what? This isn't, we can't divide, we can't do a root. Roots are when we were trying to search for the base, and here we know the base, we don't know the exponent, we don't know that value of R. So how do we deal with this? Well, that's why we have a new thing, and that's why I like this problem, is we introduce something called logarithms. Logarithms are the opposites of an exponential. So you're like, well, what's a logarithm? Logarithm is just that, it's the opposite of an exponential. Don't try to dig any more into it. It's kind of like asking, what's subtraction? It's the opposite of addition. Well, what is addition? Well, the opposite of subtraction. They're opposites of each other. That's really the only thing you have to remember about it. That's the relationship between them. So ln of 1.22, for my other 2 there, equals R times 16, right? Well, that's simple. I can grab my calculator, and there's a button on most calculators that allow me to do ln of 1.22. And in this particular case, when I do that, I get 0.2035, a whole bunch of other stuff that follows, right? Equals R16. So then I divide both sides by 16. And when I do that, I get something that's very different than 0.03. I get 0.0127, blah, 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 blah. It keeps going on forever. Right? Now, if you didn't get the exact same value using your calculator, that's fine. It's probably a little bit of round off error. I didn't use 1.22. I used the entire decimal. Okay? So just keep that in mind when you're trying to solve these things. So now I get the new value of R. So my model, my correct model, is actually P is equal to 6.2 e to the 0.0127. There's a point right there. T. That's my correct model. Okay, now you say, well, why was the model so wrong? Well, because the late 90s were very different than the 2000s. There's a lot of different economical things that were happening, population changes, plus human population can choose when and if to reproduce, which is going to change the model. So the human population growth is always going to be in a state of flux. Other populations like deer and worms or some other type of creature, or even plants for that matter, aren't. They're going to follow a model and they're pretty much going to stick to it. Humans have this ability to choose, and that's what makes this different. So what's the population going to be in 2019 according to this model? Well, 2019 is 17 years. So all we need to do is just repeat this process we did above. 6.2 e to the 0.0127 times 17. And we get our calculator, right? And we just type in that information there and we get 7.60 billion. Well, it doesn't really look like it's changed at all, does it? It's changed a little bit, not very much, but it has changed a little bit. From 7.6 to 7.603 is actually the next one there. So it's added, we've added, 300,000 or 3 million families, something like that, 3 million people. So there's definitely some growth there. And there's a lot of other things you can do with this as well. Now, I have another example, and I'll go through this one in a different video. But right now, this is what you really need to take down. I use the continuous model because human populations, creatures in general, are going to grow continuously. Populations are so huge, that's the behavior they're going to have, versus non-continuously. Now, what's the difference between these two? It's simple. It's this value of n right here, okay? How many times, and it reappears right there, how many times are we compounding, which means how many times are we refiguring how this value, what this value is. In this particular case, if we're doing it continuously, we're constantly refiguring the values, which if you think about it for a second, it makes sense with a human population or most any creatures in general. We're constantly refiguring because in general, they're not going to just repopulate or reproduce once and then they're done, or once a year. In some cases, some animals do, but human populations are going to follow a continuous model because it's almost a constant growth. There's at any time in the day you go to the hospital and a baby's being born, right? Non-continuous. Well, when are we using this one? Well, we use this one for finding the value of a home, figuring how much money you owe your credit card company, figuring how much money the bank owes you, things like this. For continuous here, we'd use this one for populations, all right? Like we've already done here. We'd also use it for radioactivity, in which case the R value would be negative. So radioactivity is a constant decay. Now, if you look in your chemistry books, you'll probably find a slightly different equation. But the thing is, you end up getting almost the exact same equation when you're done. Same thing over here. You might find small differences in equations when you look at different text, especially if you look at economics. But the idea is the values are going to be very, very close. And these two, a lot of times, are interchangeable if you just allow the value of n to be 1, or in some cases, you let the value of n to be really huge. But that's what we're looking for. Now, the other thing I want to bring your attention to is this value of e right here. Okay, that's a button on your calculator. It is defined as being 2 point blah, 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 blah. That's a decimal that goes on forever, and it's known as the natural number. Now, why is it called the natural number? Oh, that's a video in of itself. But what you need to remember is that e is the natural number, and it's approximately 2.7. And anytime you need it, you just find that button on your calculator. On the TI-84, it's right next to 4, and you do second ln. I don't know about the other calculators that are out there on the market, but that's the one I do know, and I know that keystroke. Okay, so thank you very much. If you have any questions, feel free to email me if you have that email address, or leave comments in the line below. Thank you.